Hi there, and welcome to this lesson. In this lesson, we'll be learning similar shapes, okay? And under similar shapes, we'll be learning about similar plane shapes and solids. Now, as the lesson progresses, anything you don't understand, be sure to get across to your tutor, who would be more than happy to help. And yeah, let's jump right into the lesson. So similar shapes, similar plane shapes, and solids. Now in the last lesson we learned about similar triangles. This time around we'll be learning about other similar shapes and solids. Basically, we do have similar plane shapes, we have similar solids as well. So we'll be learning about similar plane shapes and solids. Now, when you're talking similar planes, similar triangles, similar plane shapes, similar solids, they all conform to one simple law. When two figures are similar, the ratio of their corresponding sides are equal. Now this applies to plane shapes and solids. So if you have two rectangles here, and basically these two rectangles are similar, okay? They have pretty much the same shape, all right? They are rectangles with the same shape. If you look, they look very much alike. One rectangle simply looks bigger than the other. But then if you have the dimensions of these rectangles, for the smaller one you have L1 and B1, and the big one you have L2 and B2. You have L1 corresponding with L2 and B1 corresponding to B2. And by the law of similar shape, basically the ratio of L1, the length and breadth of the small rectangle, should equal the ratio of the length and breadth of the big rectangle. So what you have is you have L1 over B1 should equal L2 over B2. Similarly, if you have a cylinder here, and you have bringing dimensions for the cylinder, you have the first cylinder, you have radius R1 and height H1, and then for the second one you have radius R2 and height H2. Basically, looking at the two cylinders, we can tell that they are similar. They look similar, okay? So we assume they are similar cylinders, and basically what that means is that the ratio of the radius and height of the first cylinder should equal the ratio of the radius and height of the second cylinder. What you have is you have R1 over H1 should equal R2 over H2. So it's pretty much the same principle. We're just going to be applying that same principle across a range of shapes, okay? Different shapes. So it applies to prisms, it applies to pyramids, it applies to, okay, we have just a single for spheres. So you have, it applies to pyramids. You have, what other shapes? You can think of pretty much any shape. If you have two similar shapes, the ratio of their sides should equal each other, basically. So now we have a very unique shape in the cuboid. A cuboid has three unique sides, three unique dimensions. So the height, the breadth, and the length. And what it is you just have the corresponding side, the ratio of any two, or all two, or the ratio of any two, actually the ratio of any two corresponding sides should equal, okay? So if you look at the height, the H1 and H2 are corresponding sides, B1 and B2 are corresponding sides, so the ratio of the height and breadth should equal, of the first cuboid should equal the ratio of the height and breadth of the second cuboid. The ratio of the height and length of the first cuboid should equal the ratio of the height and length of the second cuboid. The ratio of the breadth and length of the first cuboid should equal the ratio of the breadth and length for the second. So if you pick out any two, okay, pick out any two, basically when you have two similar shapes, the ratio of the two of the sides of each of the shapes should equal, basically. So what you have is you have H1 over L1 equals H2 over L2. You have the H1 over B1 equals H2, H1 over B1 equals H2 over B2. And then you would also have that, I think we're missing one here. You should also have that L1 over B1. L1 over B1 would equal L2 over B2. Well, given what you have here, that pretty much follows. Okay, so let's go ahead and solve some examples. Pretty much what we've been doing, basically we're just going to be working with other shapes now. The same principle. So we have rectangles A, B, C, D, and PQRS are similar. CD is 3 centimeters, RS is 5 centimeters. If AD is 12 centimeters, calculate the length of PS. So we have two rectangles here. We have AD as the diagonal, so we're interested in the diagonals of the rectangles, And then basically we have CD corresponding to RS, and obviously the two diagonals will correspond as well. So basically you start off by saying CD corresponds to RS and AD corresponds to PS, and basically what you have is you have CD over AD would equal RS over PS, and when you work that you should end up with PS as 20 centimeters. So it's pretty much the exact same principle, the exact same law, the exact same relationship. We're just going to be applying that relationship across other shapes. Okay, so let's do a few more. I think we have a few. Now example 2. In example 2 we have a cuboid is 4 centimeters long, 7 centimeters wide, and 10 centimeters high. Okay, that's one cuboid. And then a similar cuboid is 25 centimeters high, and we're looking to find the length and width of this cuboid. Okay, so basically we have h1 over l1 equals h2. You really don't need to concern yourself about getting all of these down. The best way to approach a question like this, look at the question and just reason it out. So you have one cuboid 4, 7, 10, and then you have a similar cuboid something 25. Okay, so these are your dimensions. And then basically if you're looking to find we'll start off with the length. If we're looking to find the length, we have the height. We're looking to find the length of that cuboid. We establish a relationship. We'll find the ratio of the height and length for the first cuboid. So 10 centimeters and 4 centimeters. So we have 10 over 4 equals 25, the height and length of the second cuboid, 25 over something. Okay, so for the ratio of the height and length for the first cuboid, it's 4 centimeters long, 10 centimeters high, 10 over 4 equals height and length of the second cuboid, 25 over something. And with that you could find said something, and said something you should work out as 10 centimeters. Okay, to find the width, basically you look at relationship ratio of the height and width of the first cuboid. So you do 10 centimeters over 7 centimeters should equal 25 over something, and to find that something you just go ahead and solve, and you should end up with 17.5 centimeters. Simple stuff. Okay, now final example, example 3, and we have milk powder is sold in similar cylindrical tins. Okay, the small tins are of height 12 centimeters and diameter 10 centimeters. If the radius of the large tin is 7.5 cm, calculate its height. So you have two cylindrical tins. The dimensions here we have the height and the radius, so we're given the diameter in this case. So the height and radius will have that diameter, so in that case it will be 5 centimeters. Okay, so we have the height of the first tin 12 and radius 5. Okay, and the height of the second tin is what we're looking for, and we have a radius of 7.5 centimeters. Okay, so we establish a relationship between the radius and the height of the first tin. So what we have is we have R1 over H1, that gives us 5 over 12, and that would equal the ratio of the radius and height of the second tin, so 7.5 over something. Okay, and we can now go ahead and find that something, and what we have in the end is we have 18 centimeters. And that's it. Very, very simple stuff. So you can apply the law of similar figures, let's say that, across different shapes, like as mentioned. So you can work it for rectangles, you can work it for solid shapes, cylinders, you can work it for cuboids and many more. And basically what it is, something very, very interesting. Okay, so we've talked about cuboids, we've talked about cylinders. Now for cubes, equilateral triangles, and equilateral squares, cubes, and equilateral triangles, all squares, cubes, and equilateral triangles are similar shapes. Okay, every single one of them. So if you have two squares, without measuring or anything. Every square would be similar. So basically, and then every equilateral triangle would be similar as well, and every cube, any cube you can find, would be similar as well. Now, why is that? Something to think about. So yeah, that brings us to the end of this very simple, very interesting lesson. You can go ahead now and attempt questions on the worksheet. Bye for now.